Hello and welcome to my digital presentation for the SPIE conferences on photonics for solar energy systems. I already miss your faces and the opportunity to see your reactions, but I will try to make this a vivid presentation anyhow. My name is Julia van der Burgt and I'm a PhD candidate at the Amhof Institute in Amsterdam, the Netherlands. In the group of Eric Garnett focused on nanoscale solar cells. Today I will talk about the why and how of directional emission for perovskite nanocrystals with dielectric nanolenses. I will discuss why we want this, how to achieve this in theory, how in practice, and how do we prove that we made something from emitting in all directions to something that emits the light in one specific direction. We want this because it's a way to increase the open circuit voltage of a solar cell and thereby the efficiency. We do this by means of an evolutionary algorithm, and we fabricate the structures we find with 2-photon lithography, and we measure them with a newly built setup that combines a Fourier microscope and an integrating sphere. First, why directive emission, and why do I talk about emission at all when talking about solar cells? This comes from the reciprocity, that any object that absorbs light also emits light. So to have a good absorber material for your solar cell, it should also emit light. A typical planar solar cell emits light in all directions, but this is partly a loss mechanism, and if we can make it emit the light only back towards the sun, we can increase the efficiency and via increasing the open circuit voltage. On macroscopic scale, this is typically done with concentrating lenses. These focus the sunlight towards the cell, but also you can see it from the point of view of the cell that the light emitted by the cell is focused back towards the sun. However, there are some disadvantages, and I want to illustrate that with this figure. Here we simulated the performance of 3 types of solar cells using real solar spectra measured by NREL in Denver. And here we can see that when there is a low fraction of direct sunlight, which means a high fraction of diffuse sunlight due to scattering of the light by clouds, the efficiency of a macroscopic concentrating lens drastically drops, because the concentrating lens does not focus the diffuse sunlight to the cell, so you miss out all this energy. However, and that is why we focus on nanophotonic structures, there you can make the directivity wavelength dependent. A macroscopic lens focuses all wavelengths roughly the same way, but with a nanophotonic structure we can make it directive over only a narrow band to make only the emission spectrum of the solar cell directed back towards the sun, but all higher energy is still efficiently absorbed, such that we don't lose out the part of the diffuse sunlight like we see over here. And that way we find that we can increase the efficiency on a yearly basis by more than 5%. So that is why we want to go to nanophotonic lenses instead of macroscopic concentrating lenses. The definition of directivity is given here. It is the maximum intensity in some angle divided by the average intensity in all angles. So you calculate that by looking at the maximum intensity divided by the average in all directions by integrating over all angles, and in 3D that gives the full 4 pi solid angle, so you divide the total integrated emission by the 4 pi solid angle. And from that definition you can see that this kind of emission pattern corresponds to a much higher directivity than this one, because it emits much less light in other angles than the maximum. And given this definition of directivity, the open circuit voltage increases with the natural logarithm of the directivity as given here. Then, how do we achieve this kind of directivity in theory? Often plasmonic nanostructures or nanoantennas are used to create directive emission. However, for the purpose of solar cells, the parasitic absorption in the metals gives too much of a loss and high efficiencies cannot be achieved, and that's why we focus on dielectric materials that do not have this parasitic absorption. Then the question is, what kind of shape is this? Should this black box have such that all the light is emitted in one direction? For that purpose, an evolutionary algorithm has been developed, and it works as follows. It does the optimization in 2D by just generating random pixels containing material or not, and then it looks at the directivity of this random structure, and it generates a lot of them and selects the best ones, and these ones are breeding to form the next generation over and over again, and each generation has a bit higher directivity because each time the structures with the highest directivities are kept to generate the new generation, and in that way very high directivities can be obtained. These results are for an already published paper on emission in the infrared, and now we are working on structures emitting in the visible, and here we've already found a directivity of 300. The final 3D lens looks something like this, and this is obtained by rotating the 2D optimized structure around the symmetry axis to obtain this 3D structure. And the emission pattern looks something like this. Then the question is, how do we make something like this? Of course, we need an emitter, preferably one that is bright, such that we actually can detect something on our detectors. And it has to be point source-like, because the evolutionary algorithm is optimized for a point source at the center of the lens. The lens has quite a complex 3D shape that has to be fabricated from a transparent, non-fluorescent dielectric material. As the emitter, we have chosen cesium lead bromide perovskite nanocrystals because they are very bright emitters with a very high photoluminescence quantum yield, and we can relatively easily synthesize them in our own lab. And to get the point source-like behavior, I use a technique developed by a colleague of mine of direct E-beam lithography of these nanocrystals, which I will discuss in more detail on the next slide. But first about the lens fabrication. This we do with 2-photon lithography with a commercially available machine called the nanoscribe, and it works as follows. The sample has to be a transparent thin glass slide on which you put a small drop of photoresist. An infrared laser beam is focused by the objective into the photoresist, and only at the very much focus point of this laser beam, the intensity is high enough for a significant probability of 2-photon absorption, and only then the resist is exposed and structure forms, and anywhere above or below the focus the resist stays unexposed, and that way you can fabricate all kind of complex 3D structures with a resolution of a few hundred nanometers. Then about the direct E-beam lithography. My colleague Christian Dieleman has developed this. And in contrary to conventional lithography steps where you need photoresist and lift-off steps and can be quite complicated, in this case we directly cross-link the ligands that are always present on the surface of these perovskite nanocrystals upon electron beam exposure. So what we do, we just spin coat a couple of monolayers of these nanocrystals, and we expose small dots to the electron beam, and only there the ligands cross-link and bind the particles together and to the substrate. And then we wash all the other particles off with the original solvent of toluene, and what remains are these small patches of perovskite crystals in an ordered array, and that is very important for me to be able to do proper alignment, because the emitter has to be right at the center of the lens, and with this ordered array it's more easy to center the lens right on top of each of those patches. So in the end, our sample looks the following way. We have a thin transparent glass substrate such that we can illuminate it with a nanoscribe from below. For the e-beam lithography, it has to be conductive, and therefore we need a thin layer of transparent indium tin oxide, which is a transparent conductor. We pattern the patches of perovskite nanocrystals, and then we add a thin layer of alumina to protect them to the chemicals that are used later on in the fabrication of the lens. In the fabrication of the lens, the structure is also exposed to very high laser power from the nanoscribe. And if we focus the nanoscribe right at our perovskite crystals, the photoluminescence will be quenched. So therefore we use a spacer layer of 100 nanometers, such that we only start writing the lens a little distance away from the perovskite cube, such that they survive this final lens writing step. And the results look as follows. Here we have this array of lenses, and this is what a zoom in looks like on the scanning electron microscope of one of these lenses. And you can see that it quite nicely resembles the shape that came out of the algorithm. Finally, how do we prove that we made something directive? For that, I go back to the definition of directivity I gave in the beginning, where I showed that we need to know the maximum intensity into some angle and the total amount of emission. Typically, directivity is measured in a Fourier microscope that gives you the angular emission pattern, but only in the cone of the objective, and from that one can obtain the maximum power into some angle. But as I already emphasized, this only gives information about the light collected by the objective. In order to have the total amount of emission, we have combined a Fourier microscope with an integrating sphere. And it looks as follows. The sample sits on a piezo stage in the integrating sphere, and a microscope objective focuses an excitation laser on the sample with a spot size of a few micron. Part of the light is emitted back into the objective and collected through the Fourier microscope on a CCD camera, while all the light that is emitted in other directions and is not collected by the microscope objective is scattered around on the wide scattering surface of the integrating sphere until it's detected by a second detector on the integrating sphere. And this gives you the total emission outside of the cone of the objective. By combining those two signals, we can get the total emission. We had the maximum power from the Fourier microscope, and this allows us to fully experimentally measure the directivity into the 4 pi solid angle. Here are some preliminary results on this setup. Unfortunately, this is where the coronavirus kicked in and I was not able to go to the lab and do my final measurements, but there are already some very promising results. These are on a slightly different material system, where we have a nanowire underneath a nanolens. And here we see a map by scanning with the focused laser spot, moving the sample on a piezo gauge through the focused laser and collecting the signals at each position. This is the total amount of counts on the CCD detector on the Fourier microscope, and this is the integrating sphere signal. And here we already clearly see that underneath the lens, the intensity of light in the integrating sphere, light that goes to the back, is much lower compared to the bare wire. And if we look at the actual Fourier images corresponding to this map, we see that underneath the lens, from the center of the lens, there is a very narrow beaming of light into one specific direction, this bright spot here, while the bare wire shows a very uniform emission pattern of light being emitted in all directions. Also from the current material system we have some results. Here again scanning electron microscope images of the lenses. And here are the results from a bare emitter that gives very uniform Fourier image, and from a lens on top of the emitter, where we see already a bright spot appearing, but with only a directivity of 3.5. This is still far away from the directivity of 300 that we expect from theory, but this was a very first sample, and there's still some optimizations need to be done. But unfortunately I've not been able to go back to the lab since. But for example, in this case the alignment with the lens, between the lens and the emitter, was not so good, and it was not very much point source like emitter yet. It was a big chunk of emitting material underneath. So there's definitely still room for improvement here. But for now we can conclude that directive nanolenses have a potential to increase solar cell performance. We have designed with an evolutionary algorithm lenses with a directivity of over 300, and we can fabricate them with 2-photon lithography. And we have a very unique setup that is able to measure the directivity on them. So now it's just a matter of going back to the lab and combining all of this. So I'm very much looking forward to that. Thank you for your attention, and I'm looking forward to answer your questions.